Welcome to the deep dive. Today, we're plunging into something you probably use every single day, maybe without even thinking about it. Large language models, LLMs.
Right. They're everywhere now. Smart replies in email, AI assistants helping brainstorm.
Yeah,
They're just woven into how we use tech.
exactly. They understand, they respond, often sounding completely human. But what's fascinating is that under the hood, they're not all the same.
Not at all. While the core idea might seem similar, process language, their actual architectures, the blueprints, can be really different.
And those differences matter a lot.
They absolutely do. They dictate what a model is good at, how efficient it is, everything.
Yeah, like our sources point out, you've got DeepSeek excelling at reasoning, Claude being great for coding, ChatGPT nailing creative writing. It varies.
Precisely. So that's our mission today, right?
Yep. Our deep dive is into 7 of these key LLM architectures. We want to unpack what makes each one tick, what makes them unique.
And hopefully give you a clearer picture of why these distinctions are so important in the AI landscape today.
Okay, let's kick things off. Where should we start?
Let's go back to, well, almost the beginning of this modern wave. BERT.
BERT. Google, 2018. Bidirectional encoder representations from transformers. Sounds technical.
It was, and it was a huge leap. Before BERT, models usually read text just one way, left to right or maybe right to left.
Kind of like reading a book normally.
Exactly.
Yeah.
But BERT introduced deep bidirectional attention. It used something called a transformer encoder.
Okay, so bidirectional. How did that change the game for understanding language?
Well, think about it. If you only read left to right, you don't know what's coming later in the sentence when you're looking at an early word.
Right. Context is limited.
BERT could look at the entire sentence at once, both forwards and backwards, considering every word relative to all the others simultaneously.
So it could grasp nuances, like if a word's meaning depends on something later in the sentence.
Precisely. Irony, complex relationships. It got a much deeper understanding of the full context, a true understanding, you could argue, for the first time in that way.
That is a big shift. And how did they train it to do that? What did it learn?
2 really clever tasks. First, masked language modeling.
Masked, like hiding words.
Yeah, exactly. They'd randomly hide or mask words in a sentence, and BERT had to predict what the hidden word was based on everything around it, like filling in the blanks.
Okay, forces it to understand context.
Right. And the second was next sentence prediction. It had to figure out if sentence B logically followed sentence A.
So understanding flow and connection between ideas.
Yep. These 2 tasks together really pushed it to develop a rich, holistic grasp of language.
And you mentioned it uses encoder stacks. What does that mean structurally?
So the transformer architecture has 2 main parts, encoders and decoders. Encoders are designed to read and understand the input text. BERT relies only on these encoder stacks. Think of them as the analysis engine.
Got it. And they come in different sizes?
Yeah, BERT base has 12 layers, about 110 million parameters. BERT large doubles that, 24 layers, 340 million parameters.
More layers, more complexity, presumably better understanding.
Generally, yes. And it uses special tokens too, like CLS at the beginning of a sequence, to represent the whole sentence's meaning for tasks like classification, and SEP to mark the end of one sentence and the start of another.
Which it needed for that next sentence prediction task.
Exactly. BERT really set a new standard for natural language understanding.
Okay, so BERT nails understanding. But then came the models focused on generating text that feels incredibly human. That sounds like GPT.
Yes, the generative pre-trained transformer family from OpenAI, starting with GPT-1 back in 2018, same year as BERT actually, but taking a different path.
All the way up to GPT-4 in 2023 and GPT-4o just, last May, with multimodal stuff.
Right, and the core architectural difference is key. GPT models are decoder only.
Decoder only, so unlike BERT's bidirectional encoders.
Exactly. Decoders are inherently unidirectional. They'd only look at the tokens that came before the current position when they're generating the next token.
So if BERT is the expert reader analyzing from all angles,
GPT is more like the fluent writer, focused on predicting what word comes next based on everything written so far.
that makes sense. And training, how do they become so fluent?
Massive, massive data sets, pre-trained on a huge text corpora with a really simple but powerful objective. Next token prediction. Just predict the next word over and over again.
And somehow that simple task leads to complex language generation.
It does. They learn grammar, facts, styles, reasoning abilities, all implicitly from that process.
And the impact was huge. Each version got better, more fluent, and showed this amazing few-shot learning ability. What does that mean in practice?
Few-shot learning is, well, it's pretty cool. It means you can show the model just a handful of examples, maybe only one or two of a task you want it to do.
Like translate these sentences or summarize this paragraph.
Yeah, exactly. And it just gets it. It understands the pattern from those few examples and can apply it to new inputs without needing to be completely retrained. Super adaptable.
Which led to this whole pre-train and prompt idea, right? Train once, then guide it with instructions or examples.
Precisely. That became the dominant paradigm. Though it's worth remembering, GPT models are proprietary. You usually access them via an API, and OpenAI doesn't release all the architectural details, especially for newer versions like GPT-4 or 4.0.
Right, the secret sauce. Okay, so moving from closed source to more open approaches, let's talk about Llama.
Llama, yes. Large language model Meta AI, from Meta, obviously. First released February 2023, and we saw Llama 4 just this April 2025.
And this one made waves partly because it was open source, right? Or at least
Yes.
more open.
Exactly. It's a family of decoder-only models, like GPT, but released with weights available initially under a research-focused license. Sizes range from 7 billion parameters up to 70 billion.
And they made some specific architectural tweaks different from standard transformers.
They did things like using SWID-GLU activation function instead of the more common GLU. They used rotary positional embeddings, ROP instead of fixed ones, and RMS norm instead of standard layer normalization.
Okay, those sound technical. What was the effect of these changes? Why do them?
Efficiency and performance. These tweaks, think of them as internal engineering optimizations, allowed Llama models to perform incredibly well for their size.
Punching above their weight class, so to speak.
That's a perfect way to put it. The Llama 13B model, so 13 billion parameters, actually outperformed OpenAI's GPT-3, which had 175 billion parameters on quite a few benchmarks.
Wow, that's significant. Getting more bang for your buck, parameter-wise.
Definitely. And their 65B model was right up there, competitive with giants like Google's PaLM and DeepMind's Chinchilla at the time.
And the open release really spurred the community, didn't it?
Oh, massively. It combined this efficient training and performance with actual access to the model weights, leading to a huge amount of research, fine-tuning, and development from the wider community.
Okay, next up on our list is PaLM Pathways Language Model, another Google project.
Right, PaLM. The original was announced in 2022, PaLM 2 in May 2023. The first PaLM was just enormous 540 billion parameters.
That's 540 billion. That's huge even now.
Absolutely. It was also a decoder-only transformer, like GPT and Llama, and it was part of Google's bigger Pathways initiative.
Pathways, what's the idea there?
The vision for Pathways is to build a single, highly efficient model that can learn potentially millions of different tasks, kind of generalizing across modalities and tasks more like humans do. PaLM was a major step in that direction.
And training something that big must have been a challenge.
Incredible challenge. Trained on a curated, high-quality data set of 780 billion tokens. They used thousands of Google's own TPU-v4 chips, really pushing parallel processing.
And it had a feature called multi-query attention. What does that do?
It's an optimization mainly for inference, for when the model is generating responses. It helps reduce the amount of memory bandwidth needed.
So making that giant brain think faster and more efficiently when you ask it something.
Basically, yes.
Yeah.
Especially important at that scale.
And what was PaLM known for, capability-wise?
Excellent few-shot learning, again, thanks to that massive and really diverse training data, web pages, books, Wikipedia news, code from GitHub, even social media chatter.
So breadth of data was key.
Definitely. PaLM 2 built on that, improving multilingual skills, reasoning, and coding. And you see PaLM Tech powering things like Google Bard, or, well, now Gemini, and features in Google Workspace.
Which leads us nicely to Gemini, Google's next-generation family from DeepMind and Google Research starting late 2023.
Gemini is a big deal because it was designed from the ground up to be natively multimodal.
Natively multimodal. What's the difference between that and, say, GPT-4o, which also handles images?
It's about the fundamental design. Instead of maybe training separate components for text, images, audio, and then figuring out how to make them work together, Gemini was conceived and pre-trained from the start to process and reason across all these different types of information, text, images, audio, video, code, within a single unified model.
So it's not just handling them, it's integrating them more deeply.
Exactly. It can potentially understand the connections between modalities in a more fundamental way. Imagine showing it a physics experiment video and asking it to explain the concepts and generate the equations. That kind of cross-modal reasoning is the goal.
that sounds powerful. Architecturally still based on transformers?
Yes, transformer-based, built for massive scale, and supports very long context windows, meaning it can handle a lot of information at once. But a key feature, especially in the 1.5 and 2.5 Pro versions, is the use of a mixture of experts architecture. MoE.
We're hearing that term more. Can you break that down? How does it help with efficiency?
Sure. So instead of having one enormous, dense neural network where every single parameter is activated for every calculation.
Which sounds computationally expensive.
Extremely. And MoE model has multiple smaller expert subnetworks. For any given input token, the model uses a gating mechanism to intelligently select and activate only a few of these experts, the ones best suited for that specific piece of the task.
Ah, like calling in specialists instead of having the entire hospital staff work on every patient.
That's a great analogy. You get the power and knowledge of a potentially huge overall model, because the sum of all experts can be massive, but you only pay the computational cost of running a small fraction of it at any given time.
Much more efficient.
Dramatically so. It allows for scaling up model capacity without a proportional explosion in compute cost.
And Gemini has evolved quite a bit already.
Yeah, the 2.5 series came out March 2025, focusing on deeper reasoning. Then this June, we got the stable Gemini 2.5 Flash and Pro models. Flash is geared towards speed and cost efficiency. There's even a flashlight previewed. Pro is the more capable version. They boast things like million-token context windows and tool integration, like calling search or running code.
And different sizes, too. Ultra, Pro, Nano.
Right, designed to run everywhere from big data centers down to potentially on your phone. So that combination of native multimodality and efficient MoE scaling makes Gemini really flexible and powerful.
Okay, let's hop across the pond to Europe. Mistral, French AI startup, made a splash in 2023.
They certainly did. Their first model, Mistral 7B, launched September 2023, a 7.3 billion parameter decoder model. Relatively small, but mighty.
And it had some specific optimizations, too. Grouped query attention, sliding window attention.
Yep, GQA and SWA. Again, these are clever tricks to speed up inference and handle longer sequences more efficiently. GQA reduces the computation needed for the attention mechanism. Sliding window attention helps the model focus on recent context and long inputs without getting overwhelmed.
And did these help it perform well for its size?
Absolutely. Mistral 7B outperformed Llama 213B, which was twice its size, and held its own against even larger 34B models on some tasks. It was very impressive.
And initially released very openly, right? Apache 2.0 license.
Yes. Mistral 7B was fully open source under Apache 2.0, which the community really appreciated.
Then they also adopted the mixture of experts approach.
They did, with Mixtral 8x7B. That's a sparse MoE model. It has 8 expert networks per layer, each being about 7 billion parameters.
So 8 experts of 7B each. How did that perform?
Very well. Mixtral matched or beat models like GPT 3.5 and the Lamy 270B on things like math, coding, and multilingual tasks. The MoE architecture clearly delivered.
But Mistral's strategy shifted a bit recently towards proprietary models.
Somewhat, yeah. In May 2025, they released Mistral Medium 3. Its position is a mid-sized model for enterprise use, proprietary. The claim is it gets over 90% of the performance of something like Claude 3.7 Sonnet, but at a fraction of the cost per token, they quoted figures like $0 for 40 cents versus $3 for Sonnet.
A big price difference.
Huge. But yeah, the move to closed source for some of their newer, higher-performing models did generate some debate in the community about open versus closed AI development.
And they just launched Magistral, too, focused on reasoning.
Right, Magistral in June 2025, explicitly designed for reasoning tasks. Interestingly, they released a small version under Apache 2.0 again, but the high-performing medium version is enterprise-only. It shows strong results on math benchmarks like AME 2024.
So specialization seems to be a trend, too. Okay, one more architecture to cover. DeepSeek.
DeepSeek, yes. A Chinese AI company spun off from Highflyer AI in 2023, and they've really leaned into the MoE architecture.
So another MoE model like Gemini and Mixtral. What's DeepSeek's angle? How are they using MoE differently?
They seem to be pushing the sparsity of the MoE even further. Their recent models, DeepSeek V3 and DeepSeek R1, use a highly sparsely activated MoE transformer.
Highly sparsely activated, meaning even fewer experts are used per token.
Exactly. Picture this. Each layer might have hundreds of expert subnetworks available, maybe 257, for example. But for any given token passing through, the model might only activate a tiny handful, say, just 9 of those 257.
Wow. Okay. So The total potential model size can be enormous.
Over 670 billion parameters in some cases.
But the active part of the model for any single step is much smaller.
Much smaller. Maybe only around 37 billion parameters actually doing the work for each token. It's incredibly efficient, like having a vast toolkit but only picking up the one specific wrench you need for this exact bolt.
That must have a huge impact on speed and cost.
Absolutely. Significantly faster and cheaper to run inference compared to a dense model with a similar total parameter count. They also use other optimizations like SWIGLU, ROPE, and even experimenting with things like FP8 precision and training.
And the result? How do they perform?
Very strongly. Their models, many of which they've released under open licenses, are competitive with top-tier models like GPT-4, especially in areas like multilingual generation and reasoning, all while drastically reducing the compute resources needed for training and running them.
That's really impressive, achieving top performance with that level of efficiency.
It really is. It highlights how architectural innovation, especially around sparsity and MOE, is driving capability and accessibility.
What a journey through these architectures. It really covers a lot of ground, doesn't it?
It does. From BERT fundamentally changing how models understand language with bidirectionality.
To GPT popularizing large-scale generation and the pre-trained prompt paradigm.
Then Llama, showing the power of open models and architectural optimizations.
PuMLM pushing the limits of scale.
And now Gemini, Mistral, and DeepSeek really pioneering multimodality and these super efficient mixture of expert designs.
It's amazing how quickly things have evolved.
It really is. And the key takeaway, the so what for you listening, is that these aren't just minor technical details.
Right. These architectural choices are fundamental.
They directly influence what a model is good at, how fast it runs, how much it costs to operate, and even who gets to use it open source versus proprietary API. Understanding this helps make sense of the different AI tools out there.
Definitely. So maybe the final thought to leave you with is, what does all this mean for the future?
Good question. Where does this relentless push for efficiency, for multimodal understanding that mirrors our own senses, for specialized reasoning, where does it lead?
What new applications become possible when models can see, hear, reason, and generate, all while being potentially cheaper and faster to run?
And how will this constant innovation in the very blueprints of AI continue to reshape our world? That's something exciting and maybe a little daunting to think about.
Indeed. A lot to ponder as we continue this deep dive into AI.